Hello, these are Chapter 7 conceptual questions, and these all deal with action and reaction pairs. First one says, suppose you actually accidentally drive into a tree. Which of the following correctly describes the interaction between the car and the tree? And the answer here really has to do with Newton's. So it's Newton's third law. Remember, for every action, there's an equal and opposite reaction. So the tree exerts a force on the car, and the car exerts a force on the tree in the equal and opposite direction. For number 2, says forces always occur, and they do always occur in pairs. So if I push on you, you push on me in the opposite direction with the same amount of force. For number 3, it says, according to Newton's third law, if you gently push on something, it will push gently back on you. So if I'm pushing this box and I'm pushing it to the right, you see that, then the box pushes me to the left with the same amount of force, so very gently. Number 4, a woman weighing 550 newtons sits on the floor. She exerts a force on the floor, so her force on the floor will be 550 newtons. That one's pretty easy. Next question says, a 600 Newton woman sits on the floor. It says the floor exerts on her a force, so the force back up on her will be 600 newtons because they are equal and opposite. For number 6, it says whenever an object exerts a force on another object, the second object exerts a force in the same magnitude but in the opposite direction of that object. And this one is always true. So that one's never false. Number 7, as a ball falls, the action force is the pull of the Earth's mass on the ball. So the Earth is pulling the ball down this way. What is the reaction to this force? Well, believe it or not, the action-reaction force here, the reaction force is the ball pulling on the Earth. And they pull on each other with the same amount of force. But because the Earth is so big, it doesn't feel the pull of the ball as much as the ball seems to feel the pull of the Earth. But they are equal. Those are 100% equal. So the reaction to the force is the ball. Whoops. Is the ball pulling on the Earth, and it is an equal force. For number 8, a person is attracted toward the center of the Earth by a gravitational force, 440 newtons, the force with which the Earth is attracted to the person. So remember, here the person is getting pulled down by the Earth, 440 newtons. So the person pulls the Earth up 440 newtons. But because the Earth weighs a lot more than 440 newtons, we know that it doesn't have as much of an accelerating effect. Person gets accelerated straight down. Number 9, an unfortunate bug, ooh gross, there it is. A little bit better picture here, splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is the same. They have the same force. The car can withstand a lot more force than the bug can, so the bug gets swooshed. Number 10, an unfortunate bug splatters against the windshield of a moving car. Compared to the, check this out, this is different, the deceleration of the car, the deceleration of the bug on number 10 is much larger. So the bug acceleration, and remember it's negative because it's deceleration, so we can either do that or we can just say it is the deceleration is huge. And it's huge because if the bug is here flying into the windshield and the windshield is here, the windshield keeps going and the bug then ends up on front of that windshield and now it's moving the opposite direction. So the deceleration of the bug is huge. It's very large compared to the car. Number 11, a large truck and a small car traveling the same speed have a head-on collision. The vehicle to undergo the greater change in velocity will be the car, because the car, even though they have the same force acting on them, the car will go basically to almost 0, and it might even have a negative speed when it's done. If the car is originally moving in this direction at 55 and the truck is traveling at 55 in this direction, it might actually make the car go back the other way, and we could say the car's new speed is -10 and the truck speed is 45. When we look at momentum, we'll look at this a little bit more, but the car definitely undergoes a bigger change in acceleration or velocity. A high school student hits a nail with a hammer. During the collision, there is a force on the nail. That's pretty easy to see. But there's also the same force on the hammer. So those two forces are equal and opposite. There's a force on the nail and there's a force on the hammer itself. So both of them have that force. Number 13 says, here we go. Number 13 says Earth pulls on the moon, so the Earth is pulling on the moon. And similarly, the moon pulls on the Earth. This is evidence that they are simply pulling on each other. So they are simply pulling on each other. And this is an action-reaction pair. And my wife is emptying something in the sink. Number 14, Nellie Newton holds an apple in her hand. If the action is the Earth pulling the apple down, then the reaction is not the hand. It is the Earth getting pulled by the apple. So it is apple getting pulled by the Earth. And so what I do is I write down the two things and then just put a double arrow in between them. We ignore the hand. The hand just kind of gets in the way. So the apple's being pulled by the Earth and the Earth pulls on the apple. A little bit of both. Number 15, Bronco the skydiver falls toward Earth. So he is falling towards the Earth. If the attraction of the Earth on Bronco pulls him down, the reaction of the force is Bronco pulling him up. So Bronco pulls the Earth up. But because the Earth is so big, we don't notice it. Number 16, a force is exerted on the tires of a car to accelerate the car along the road. The force is actually exerted by the road. The road has to exert, a force. So the Earth, this is the road. No, it just doesn't want to behave. The road actually exerts a force on the tires. If it didn't do that, your car wouldn't go anywhere. Number 17, a rocket is able to accelerate in the vacuum of space when it fires its engines. The force that propels the rocket is the force of the exhaust gases. Here we go again. So the exhaust gases are actually pushing on the rocket when the rocket pushes the exhaust gases out. So even though they're a gas, they can do that. Number 18, a karate chop delivers a blow of 2,300 newtons on a board that breaks. The force that acts on the hand is also 2,300 newtons. So there's 2,300 newtons on the board, and then that 2,300 newtons is also coming back on the hand. So both of those are the same, and the board does break then. Number 19, an archer shoots an arrow. Consider the action force to be the bowstring. So here's the bowstring against the arrow. So there's a force in between the two where the bowstring is pushing on the arrow. The reaction force is the arrow pushing on the bowstring. So the reaction force is the arrow and it is pushing on the bowstring. Number 20, a player catches a ball. So here's a player catching a ball. Consider the action force to be the impact of the ball on the glove. So the ball comes in and hits the glove. The reaction force would be the glove on the ball. So if we remember, we can just say glove, put a double arrow, put ball, and then that way you have your action and reaction force. And then you can also do it the other way, action and reaction. Number 21, suppose two people, one having 3 times the mass of the other. So we'll say that this kid has 3 times the mass of the dog, and the dog only has 1 times the mass. It says they are pulling each other, so when they pull each other, they both go towards each other. The thing that they want to know is after a brief time they meet. The more massive person, so that would be our person here, slides a distance of, and this one, because he has 3 times the mass of the other, and he pulls on opposite sides of a 20-meter rope, so we know that the rope here is 20 meters. We know that he pulls himself 5 meters, and the other object pulls itself 15 meters, because 5 times that 3 would be equal to 15. And that's why your answer is 5 meters for him, 15 meters for the other object, because it can pull a lot faster since it doesn't have as much mass. That one's a little bit tougher. Number 22, player hits a ball with a bat. The action force is the impact of the bat on the ball. The reaction force is the ball hitting the bat. So the reaction force is the ball hitting the bat. So you've got to have both of those things happening for that ball to go anywhere. Number 23, 2 people pull on a rope in a tug of war. Each pulls with a 400 Newton force. So this person is pulling this way with 400 newtons. This one pulls this way with 400 newtons. They don't cancel themselves out. It's just the tension in the rope is 400 newtons altogether. When we do some problems, we'll talk about that one a little bit more. Number 24, if I exert a force of 12,000 newtons on a 3,000 kilogram car, and I do the same thing on a truck, and that truck is 6,000 kilograms, they want to know what is the acceleration of each one. So we got to remember F is equal to ma for each one. So this one is F is equal to ma. We know the force here is 12,000. That's equal to 3,000 times A. And then on this side be 12,000, and that's equal to 6,000 times A. So our acceleration for the acceleration for the car will be 4 meters per second squared, and then the acceleration for the truck will be 2 meters per second squared. And that is the answer to number 24. For number 25, if a horse pulls on a wagon at rest, the wagon pulls back equally on the horse. Can the wagon be set into motion? And the answer is yes, because there is a net force on the wagon. That net force comes from the horse is pushing on the ground this way, so the ground pushes the horse this way, and that force then helps push the cart in that direction. We'll look at that one again. Number 26, if your car runs out of gas, why can't you push on the car's windshield from inside? You have to have a force on the car from the outside of the car. So using your feet to push on the windshield won't do anything because those are on the inside of the car. Finally, number 27, you drive past a farm, you see a cow. So here's a couple of quote-unquote cows. They're really not cows, but we're going to pretend they are. They are plowing a field. You just learned about Newton's third law, and you wonder how the cow's able to move forward if the plow is exerting an equal opposite force on the cow. The best way to explain this is the force that is exerted by the cow, or in our case here, exerted by the cows. The force exerted by the cows on the plow has got to be smaller than the force that the cow exerts on the ground. And because those are unbalanced forces, so here the cow is exerting a force on the ground, and the ground exerts a force back on the cow. And then the plow and the cow, this is a much smaller force. So right here we would have a much smaller force. It just wants to do that every time, doesn't it? So there's a much smaller force between the plow and the cow than between the ground. So let's just make this one a little bit bigger, and the cow. And that's the end of Chapter 7.